In a previous video, we discussed various techniques for determining whether a given sequence converged or diverged. In this video, we're going to look at some additional examples of sequences and determine whether they converge or diverge. In particular, we're going to look at the sequences a sub n equals 5 cosine n over n squared, b sub n equals 5n squared plus 1 over e to the n, c sub n 3n cubed minus 2n squared plus n over 5 minus n cubed, d sub n equals the square root of 2n plus 1 over 5n plus 3, e sub n equals negative 1 to the n plus 1 times n, all over 3n plus 1, and f sub n equals the natural log of n plus 1 minus the natural log of n. It is recommended that you pause the video and try to determine whether each of these sequences converge or diverge on your own first. Then you can resume the video, and the solutions for all six sequences will appear in just a few seconds. For our first sequence, a sub n equals 5 cosine n over n squared, we're going to use the Squeeze Theorem because we know the values of cosine n are always bounded between negative 1 and 1. So we start with that inequality, that cosine of n is bounded between negative 1 and 1, and try to reproduce our sequence in the middle of that inequality. We can do that by first multiplying all three parts of the inequality by the number 5, and then dividing each part by n squared. And that gives us negative 5 over n squared, less than or equal to 5 cosine n over n squared, which is in turn less than or equal to 5 over n squared. The two sequences on the outside of our inequality, negative 5 over n squared and positive 5 over n squared, both converge to 0 as they have the form of a constant over a power of n. And as n gets large, the denominator gets large, and 5 or negative 5 over that denominator approaches 0. Since 5 cosine n over n squared is bounded between those, and both of the lower and upper sequences converge to 0, the Squeeze theorem says the limit of our sequence converges to 0 as well. Our second sequence, b sub n, is given by the term 5n squared plus 1 all over e to the n. When we go to compute the limit as n approaches infinity of that expression, we first observe that the numerator, 5n squared plus 1, will go to infinity, as well as the denominator e to the n, which will also approach infinity. And so here we have an infinity over infinity indeterminate form, and so we can apply L'Hopital's rule to this particular limit. This tells us that this will equal the limit as n approaches infinity of the derivative of 5n squared plus 1, or 10n, in the numerator, and the derivative of e to the n, also e to the n, in the denominator. We can then consider this limit, and we again observe that the numerator 10n approaches infinity, and the denominator e to the n approaches infinity as n gets large, and so we can apply L'Hopital's rule a second time to this new limit. Now we have that this is equal to the limit as n approaches infinity of the derivative of 10n, which is 10, divided by the derivative of e to the n, which is e to the n. Since n is getting large, so is e to the n, and so we have an expression 10 over a very large number, and that will approach 0. And so our limit of our sequence here for b sub n will converge to the value of 0. Our third sequence, c sub n, is given by the rational function 3n cubed minus 2n squared plus n all over 5 minus n cubed. Since we have a rational function, one approach to finding the limit of this sequence is to multiply and divide by 1 over n cubed, which will effectively divide every term in our sequence general term by n cubed, resulting in the limit as n goes to infinity of 3 minus 2 over n plus 1 over n squared, all over 5 over n cubed minus 1. The three terms that have an n squared, or n cubed in the denominator with a constant in the numerator will all have a limit of 0, since they're a constant over a power of n, and n is getting large. What's left is simply the limit of the constant 3 over negative 1, which is negative 3, and therefore by the limit laws, our sequence c sub n converges to negative 3. Our fourth sequence is d sub n equals the square root of 2n plus 1 over 5n plus 3. Here we have a simpler sequence, 2n plus 1 over 5n plus 3, sitting inside the square root function. When we have the limit as n approaches infinity of such a situation, as long as our function, in this case the square root, is continuous at our limiting value of the inside sequence, we can bring the limit inside our continuous function. And that's exactly what we do here. We can rewrite this limit as n approaches infinity of d sub n as the square root of the limit as n approaches infinity of 2n plus 1 over 5n plus 3. We can then take the limit of this simpler sequence. We could either multiply and divide by 1 over n and use limit laws, or in this case it's quite simple to use L'Hopital's rule. Since 2n plus 1 and 5n plus 3 both go to infinity, we can take the derivative of the numerator and denominator separately to get the limit as n approaches infinity of 2/5, which is just the constant 2/5. And since that is a positive number, the continuous function theorem says that everything we did here was valid, and so this sequence converges to the square root of 2/5. Our fifth sequence, e sub n equals negative 1 to the n plus 1 times n all over 3n plus 1, has an alternating negative sign involved, the negative 1 to the n plus 1. Whenever we have such a sequence, we can always take the absolute value of the sequence term and take the limit of that, and use the absolute value theorem to determine what happens with our given sequence. In this case, when we take the absolute value of negative 1 to the n plus 1 times n, all over 3n plus 1, we get rid of the negative 1 to the n plus 1, since the absolute value will make that term always equal to positive 1, and we have the limit as n approaches infinity of n over 3n plus 1. Using L'Hopital's rule, this is the limit of a constant 1/3, which will of course equal that constant of 1/3. Here we note that 1/3 is not equal to 0, and so the absolute value theorem says the limit as n approaches infinity of our original sequence term, negative 1 to the n plus 1 times n over 3n plus 1, does not exist. In this case, this means the sequence diverges. The absolute value theorem says that as long as the limit of the absolute value sequence is not 0, the sequence that we started with will always diverge. And last but not least, we have our sequence f sub n equals natural log of n plus 1 minus natural log of n. In this case, although it might not be the first step that we try, what we ultimately will need to do is to rewrite the term of our sequence using properties of logarithms. In this case, we have a difference of 2 logarithms, and so by the quotient rule of logarithms, we can rewrite this as the natural log of n plus 1 divided by n. When we take the limit as n approaches infinity of natural log of n plus 1 over n, we can use the continuous function theorem to bring the limit inside the natural log to obtain the natural log of the limit as n approaches infinity of n plus 1 over n. We can easily compute that limit to be 1 using either limit laws or L'Hopital's rule, and so the continuous function theorem says that our limit is equal to the natural log of 1, which is equal to 0. And so this is a convergent sequence, and it converges to the number 0. Note that if we did not rewrite this expression at the very beginning, using properties of logs, we might have tried to use the limit laws in this case. If we did try to use the limit laws, we would have the limit of the natural log of n plus 1, which would be infinity, minus the limit as n approaches infinity of the natural log of n, which would also be infinity. And we would get the expression infinity minus infinity. And while you might think that this is equal to 0, which is in fact the correct value for our limit, there are many, many cases where infinity minus infinity is not 0 because infinity is not actually a number. It's a symbol that's used to describe the behavior that the expression is getting extremely large. And so here, infinity minus infinity should not in any way be interpreted to be 0. There are examples like this where we might have a difference, and using the limit laws will give us infinity minus infinity, and the value will not converge or will converge to some value other than 0. And so this expression in red at the bottom of our screen now makes absolutely no sense. It's worth noting that the limit laws only apply when the limit of the sequences that are being combined together converge. And in this case, the limit of the two individual sequences, natural log of n plus 1 or natural log of n, both diverge, and so the limit laws would not apply to this particular example.